Okay, welcome to your Chapter 15 introductory videos. So what's going to happen here is your next exam will cover Chapter 15, but there'll also be parts of Chapter 16. So this video will be most of Chapter 15, about 3/4 of it, and the last part of 15 and the part of 16 that you'll be responsible for. We're not covering 16 in great detail. There's a couple key concepts there that we agree on faculty to include. So both of these chapters are going to deal a lot with acid-base equilibria, and the title of this chapter then is Acid-Base Equilibria, Proton Transfer in Biological Systems. Here are your learning goals, and these are learning goals for chapter 15 and 16. Identify and characterize acids and bases, handle calculations involving all of these. We'll learn about all of this. We're going to be using Rice tables, so if you mastered that in the last chapter, you're in good place right now. These are just equilibrium constants. And you'll notice there are lots of different equilibrium constants. We just changed the superscript there, as the subscript there, to designate what specifically we're talking about. You'll see that down here also with a KSP. So there's several that we'll learn, but they are treated all the same. You'll also need to be able to predict whether a salt solution is acidic, basic, or neutral. Now your book does some calculations on that. You're not responsible for the calculations. You're just going to be able to identify the salts and tell whether the solution would be acidic, basic, or neutral. This is where Chapter 16 comes in, down here. Know basic terminology and characteristics of buffers and titrations. I'll also ask you, before we get to that section, which will be not until the second lecture, is to review Section 8.7 in your book. That's when some of this terminology for at least titrations was introduced. Lastly, understand the solubility product, both conceptually and being able to do calculations with that concept of either calculating solubility or the KSP. So here's the chapter outline, and this is where I will stop on this video. And then those last two sections will be part of the second video and along with chapter 16. So acid and base balance. This is interesting here. This is the buffering system in the human blood. And it's interesting to note that it's the same buffering system that is in natural waters. So a little bit of interesting information in that, theoretically we are believed to have evolved from water, and it's kind of interesting that we have the same exact buffer in our blood as that are found in our natural water systems. So what you see here is carbon dioxide reacts with water to form H2CO3. This is known as carbonic acid. So it's an acid, obviously. And CO2 is an acid. And this is one of the problems with climate change. One of the lesser known problems, that is acidification of oceans, because the oceans absorb most of the CO2 that's put out there. So what can happen now is this carbonic acid, H2CO3, can actually react with water and form HCO3 minus plus H3O positive. And this is what we'll define as we go through the semester as the key to what makes something an acid. Able to donate one of its protons. See, what it has done here is taken one of these protons here and donated it to water, forming this species right here. That's really what we think about it as an acid. Now, your body is capable now of actually kind of neutralizing any base that presents itself. Because this is an acid and this is an acid, this can neutralize a base. And neutralization reactions are pretty simple. I'll write it in the simple form. An H positive that's generated from an acid and an OH negative that's generated from a base can basically combine to form water. So this, if you will, is kind of the key component of a base, hydroxide, where the H positive is the key component of an acid. So what you can see is actually our bodies are capable of neutralizing this. And you can also think about Le Chatelier's principle here. If too much CO2 gets into the system, too much acid is produced, we get a condition called acidosis. The system can also come out of balance, and you can have not enough acid or too much base in the system and have alkalosis. So the pH of our blood is very closely buffered and very in a very small range. Forget exactly what that is. Something like 7.3 to 7.4, something right around in that range. So an acid, a compound that produces hydronium ions in aqueous solution. That's what we just saw. And another way of looking at it is that it donates H positive, where a base is the compound that produces OH negative in aqueous solution, or if you will, another way of looking at that is accepts H positive. There are several definitions of acids and bases. There's Bronsted-Lowry, there is Arrhenius, and there is Lewis. You should be comfortable with really those definitions, not being able to distinguish which one is which, but to know that an acid is a proton donor, but also an electron acceptor. That's one of the key other definitions of it. And that'll become more important as you move on in your chemistry training. And a base then is just the opposite, a proton acceptor or electron donor. Now, one thing that's important is acid and base strength. And when we talk about strength, it's nothing to do with concentration. Concentration are two different things. I can make an incredibly dilute solution of a very strong acid and you can drink it. I can make an incredibly concentrated solution of a very weak acid and it'd be dangerous to drink. So it really has nothing to do with concentration. So you look at this reaction here. We use HA to represent kind of a generic acid. Okay, you got the H positive and the A stands for the anion that's produced. Reacts with water, you get your A negative and H3O positive. Okay, that's your basic acid there. We can write an equilibrium constant for that. We're going to call this Ka now to signify an acid dissociation reaction or ionization of the acid. And we got products over reactants, so H3O positive, H negative over HA. Now, what we mean by a strong acid is that this is greater than 1. In fact, I would argue and say that it's much greater than 1 for a strong acid. Common strong acids, things like hydrochloric acid, your halogens base. You can list all your halogens there. You can also, so hydrobromic acid, hydroiodic acid. Also, I'm sorry, you cannot list HF. HF is not a strong acid, and we'll come to why that is later. But H2SO4 is a strong acid. Nitric acid, that's sulfuric acid, nitric acid, HNO3. These are all strong acids. You need to get somewhat familiar with these. There's tables in your book. You need to somewhat memorize them because by memorizing them, then you can recognize when something is not a strong acid and is a weak acid. And that'll be important in how you treat it mathematically. So basically what we say is a strong acid, and that's why we've drawn this arrow like this, the degree of ionization is substantial. And if we were to look into solution and analyze this right here, we will find little to none of that remaining. And that's the key for a strong acid or strong base. And this is just listing a couple strong acids. And here you see them. These are the ones that you need to be familiar with and recognize. So commit those to memory. Now let's see. This right here, following in the same reasoning, the smaller the Ka, the weaker the acid. So this is a weak acid now, and this is going to be less than 1. So effectively, you can say the smaller the Ka, the weaker the acid. Smaller the Ka, weaker acid. Applies to bases too. For a base, you can simply write, HB plus H2O goes to H2B plus OH minus, something like that. Or, it could start as B negative. B negative plus water gives you HB plus OH negative, something like that. Oops. That's right, I did that right. So that's very similar to an acid. And this is just showing you some weak acids now. Acetic acid is the classic weak acid that we use for all our examples and talk about. So that's just giving you an example of some of those. You don't have to memorize those, because what you're going to do is memorize the strong ones, and if it's not strong, you're going to assume it's weak. Now, we don't cover organic acids, so these are all going to be inorganic, basically. Here's some oxoacids, and one of the keys here is that oxidation number is something that was introduced in Gen Chem 1, but really we'll come back to in actually Chapter 17. The greater number of oxygen atoms, the stronger the acid. So, and you see here, based on the Kas, HClO4 is a strong acid. HClO3 is not considered a strong acid, but it's pretty darn strong. This one here, weak acid, and even much weaker acid. So the key here is that if you were to look at something like this, compare these two, the oxidation number really is the kind of theoretical positive charge that resides on that central atom. And we talked about this in Gen Chem 1, how to calculate that. I'm not going to go through this right now. I'll talk about it in class. But in this case, it's +6. And let's see, is that right? Yes, it's +6 there. And this is +4 here. So the higher the charge, if you will, the greater the positive charge, stabilizing each of the oxygens. Another way to look at it is that the anion that's produced the greater number of oxygens helps to stabilize that in solution. So there's two things to look at really when we talk about the strength of an acid. Two things that really dictate that. One is how easy the hydrogen can leave, and that is the strength of the bond. Also, how stable the anion that's produced is. Those are two things that really are going to dictate whether an acid is strong or not. So here's some right here. And we see in this case, there's a clear trend here. And if you recognize this trend, you would look at the halogen and you'd say, what's happening in this direction is increasing electronegativity. Increasing electronegativity, we also symbolize En. Chlorine being the most electronegative. It's pulling, if you will, the electron density away from the hydrogen and therefore making it easier to leave. Okay, so those are some of your oxoacids there. Moving on, strong and weak bases. Everything we talk about with acids can be applied to bases. Okay, your strong ones for bases are basically your group 1 and group 2. It's just important to realize that in group 2, of course, you have 2 hydroxides that can dissociate. So group 1 would be something like sodium hydroxide, very strong base. Group 2, calcium hydroxide, very strong base, but of course it has 2 hydroxides it can release. That's not anything to do with the strength. The strength is the degree of ionization, but it can produce 2 hydroxides for each mole that's added. So it's going to obviously have a greater effect on your basicity, your alkalinity of your solution. Also, some species, when you look at them, you might not think of them as bases because you don't see a hydroxide there. But your ionic oxides, they can produce hydroxides by reacting with water. So this what we'll do, we'll react with water, this calcium oxide, form calcium 2 plus ions plus 2 OH minus. And that's how the base is produced here. But you don't actually see the hydroxide in the original formula. So looking at this, you might say, well, no, that's not a base. It's important to understand the chemistry then and what happens in the reactions once it's added to water. These are the strong bases. and basically group 1 and group 2 bases. And if you memorize these, then anything else you can treat as a weak base. Okay, so weak bases produce hydroxide ions but reach equilibrium before all the bases consume. That's the idea here. It's going to produce very little of the hydroxide if it's weak, and a lot of it if it's strong. Now, here's another compound. When you look at it, you don't realize it's a base, ammonia, because you don't see a hydroxide there. But based on the reaction with water, it produces NH4 positive and OH minus. So now we're going to use B instead of A, and we can write an equilibrium constant. I'm going to take the products, NH4 positive times OH minus, using my square brackets, which means concentration, over NH3. I can ignore the water because it's pure liquid water. And this equilibrium constant is 1.76 times 10 to the minus 5. We call this a Kb instead of a Kc. And that is an equilibrium constant. Like any equilibrium constant, is the ratio of products to reactants. You might have guessed that it's going to be much less than 1 because it is a weak base. Now I want to talk a little bit about conjugate acid-base pairs. So this is somewhat obvious in the sense that when an acid reacts, okay, it donates that hydrogen ion, right? And then what's left over is the anion here. So this is the acid here, and the hydrogen has gone from here to, of course, to the water here to form H3O positive. We call this here the conjugate base. So effectively, this reaction is reversible. This is an equilibrium arrow here. This conjugate base is capable of picking that hydrogen ion off of there, or, if you will, if acid comes into solution, it can absorb that hydrogen ion, and we can move in this direction. We can effectively neutralize or take up a hydrogen ion. We can work in the opposite direction. Effectively, this would be acting as a base, because the definition of a base is a proton acceptor or hydrogen ion acceptor, right? Another definition is a hydroxide donor, but a hydroxide, if you will, can accept the hydrogen ion and neutralize it. This is what I said on the very first slide, a neutralization reaction. There's your base, there's your acid. So the acid produces a conjugate base, and of course, in every acid-base reaction, there are pairs. This is serving as the base here. What's it doing? It's accepting the hydrogen ion. It's a base, therefore this is the conjugate acid of that base. So each base forms a conjugate acid, each acid forms a conjugate base. They only differ by one proton, by one hydrogen ion. That's what makes them a conjugate pair. This is not a conjugate pair because they differ by two hydrogen ions. The conjugate pair for this would be this. And of course, it would just be -1. Okay? The conjugate pair for this one, if you will, and this can be a conjugate pair. These two are conjugate pairs now. Difference of one hydrogen ion. Now, this is an important concept, the relative strengths of conjugate acids and bases. HCl is a strong acid, okay? And there's the reaction. And in fact, for something like HCl, we typically do this. We don't draw an arrow like that because the equilibrium lies very far to the right. So that's commonly done. You saw that in some points of slides and sections of the book. Effectively, the reverse reaction doesn't happen, which means the chloride ion is an extremely weak base. Right? If this is a really strong acid, this is a very weak base because the reaction doesn't go in reverse. For this to act as a base, it has to pick up a hydrogen ion from water and move in this direction, right? To form HCl and H2O. It's not going to happen with a very strong acid. And the same thing can be said about bases. Very strong bases have weak conjugate acids. That's a really important concept that'll be coming up more in lecture. Okay, the last thing I'm going to talk about is pH and the autoionization of water. So what's interesting is that water naturally does this, and that is reacts with itself to form H3O positive and OH negative. So these are normal components of just pure distilled water. Happens to a very small extent. In fact, we can write an equilibrium constant for this. Products over reactants, right? What are you going to put? Well, there's going to be no reactants, right? Because they're all pure water. So only the products are factored in. This is equal to 1 times 10 to the minus 14. That is the equilibrium constant, and it's called Kw for autoionization of water. So this is always the same with water. That's the Kw for water. So effectively, the product of these two is always equal to 1 times 10 to the minus 14. So as this one would increase in concentration, this one needs to decrease in concentration. That is this inverse relationship. So that your equilibrium constant can always be 1 times 10 to the minus 14. Because remember, equilibrium constants do not change except for temperature. So by changing these concentrations should not change my equilibrium constant. But for order for this value to be held true, if I increase this, this has to decrease. The product is always 1 times 10 to the minus 14. So for acidic solutions, you have this holding true. Basic solutions, this holding true. And neutral solutions is when they're equal. These two are equal, and then, of course, 1 times 10 to the minus 7 times 1 times 10 to the minus 7 is equal to your equilibrium constant, which is what we were just talking about here. Product of those two is 1 times 10 to the minus 14. They're always going to be equal to 10 to the minus 14. It's just here they happen to both be 1 times 10 to the minus 7 because they're equal. But here they're still going to equal. The products are still going to equal for these 1 times 10 to the minus 14. With that brings us to the pH scale, which you've all heard of and are familiar with. So here is the scale. Actually, it runs outside of 0 and 14, but that's the common pH scale. And it's got some components here that tell you, natural rainwater and various things drain cleaner. pH now can be calculated as the negative log of the hydronium ion concentration, and a lot of people will just write the hydronium ion concentration as this for shorthand. They are the same thing. The POH, P just stands for basically negative log. OH, the hydroxide concentration, is going to be the negative log of the hydroxide concentration. Now remember, Kw is equal to 1 times 10 to the minus 14, and that's equal to the product of these two. Right? Therefore, what I'm going to do is I'm going to take the log throughout this equation. I'm going to take the log of everything. The negative log, sorry. I'm going to wind up with the negative log of Kw is equal to the negative log, I'm going to write this in shorthand now because I'm running out of space, H positive instead of H3O positive, times OH minus. And that negative log is times the whole thing, obviously. Well, the negative log of Kw, the log of 10 raised to the 14th power, of course, is just 14. So the negative log of 10 to the minus 14 is just 14. That's equal to the negative log of hydronium ion. We just define this right up here as the pH. So I'm going to write this as pH. And if you know your rules of log, since it's negative log of a multiplication factor here, it becomes plus here. And the negative log of the hydroxide is the POH. So the pH plus the POH equals 14. These are all useful equations here for solving acid-base pH problems. So you'll need to, get comfortable with this equation, this equation, this equation, and ultimately this form of the equation if you take the negative log throughout. I believe that's my last slide, and that brings us to about almost 25 minutes, so it's a good place to stop and look for the second video, and please watch this video before class.